So once again, good morning to all the participants. I would like to thank you also for giving your time. So in this lecture, I'll be covering about X-rays, how it is generated and what is continuum and characteristic spectra, and how X-ray is emitted from different elements, XRF and its instrumentation. And most importantly, I'll be talking about analytical methods. We know X-rays are short wavelength electromagnetic radiations, and they are produced by deceleration of fast moving electrons. And in fact, the wavelength of X-rays are very important, and the wavelength is lying in the range of atomic order. So that is the important characteristics which gives a facility for us to analyze its chemical composition or its atomic structure, or in a way you can say crystal structure. So X-rays are generated by various methods. Either you can bombard a metal with an electron beam, high energy electron beam, or you can expose the metal with the X-rays, which can generate a secondary X-rays can be generated, or we can use radioactive sources, or we can use synchrotron radiation. So X-ray tubes we have already studied in all the basic text. We have studied about all how X-rays are generated, how the spectrum is coming out from here. So electrons are produced from a cathode. So basically it is a heated cathode. So when these fast moving electrons are impinging on the target material, and which produces X-rays. So almost about 0.1% of the energy is converted into X-rays. And this X-ray is very important for us for our analytical purpose. So when X-ray is incident on a specimen, number of events will be taking place. So most of the X-rays will be converted into heat. Almost 99% of the X-rays which is absorbed by the specimen will get converted into heat, and partially it will be converted into fluorescent X-rays or scattered X-rays or electrons. So based on this, we have different tools, whether you can call it as XRF technique, XRF or XRD or electron methods. So basically, if you look into the X-ray spectrum, you can see there are two characters will be very clearly obvious to us. One is continuum spectrum, another is characteristic spectrum. So basically all the basic details, I don't want to go very detailed into that because the time is restricted for us. And the electronic transition, when X-ray is incident on a material, so electronic transition happens. So all the how the electronic transition is taking place, already Dr. Ajita has explained very clearly. So this electronic transition gives rise to what is called X-rays. This is the inherent character of a material. If this X-ray is coming from iron atom, or X-ray is coming from a cobalt atom, or X-ray is coming from calcium atom, or X-ray is coming from uranium atom, whatever it is. Now, this X-ray will be different. The character of the X-ray will be different. Now, this is the tool we are going to use to find out who is that person. That is, what is that element is of. So whether it is calcium or it is a chromium or iron or nickel, whatever it is. So you can analyze this from this characteristic spectrum. So basically, if you look into this diagram, so basically there are charts are available, X-ray, XRF charts are available. If you look into this XRF charts, so you can see there are 4 numbers around each element. So this numbers actual is designating about K alpha 1, K alpha 2, K beta 1, sorry, L alpha and L beta. So these 4 numbers are reflected. So basically that is about energy of the X-rays emitted. So for example, if I take say titanium, and that I'll just magnify this for your convenience so that you can very clearly see that. Let us take an example, let us take titanium, and around titanium you are able to see 4.151, 4.93, 0.45, 0.46. And what is these numbers? These numbers are energy of the X-rays emitted by titanium. So K alpha line and K beta line, L alpha, L beta line. So similarly, if I analyze vanadium, the K alpha will be radiation will be having an energy of 4.95. Whereas if I analyze chromium, the K alpha line will have an energy of 5.41. Manganese 5.90. So you can very clearly see that the energy of X-ray which is emitted from an element is different. So that is the primary tool or the basic from which we are going to characterize or we are going to identify what is the element is of. And the X-ray will be emitted by there are basic relationships are there, and these relations are in accordance with the atomic number. And this X-ray which is coming out can be used for a number of applications. You can use it for various purposes. Accordingly, the X-ray analytical techniques are classified as XES or AES or XFS or SCA techniques, X-ray absorption techniques, X-ray diffraction techniques. And in general, say commonly we use X-rays in medical application. So in medical applications, X-rays which are absorbed or transmitted is used for identifying the material. So in medical applications, whereas if you want to identify the structure, what is the atomic arrangement or what is the crystal structure of the material, you need to look into the diffracted pattern, how X-rays are diffracted from a crystal. So that will give you information about the crystal structure of the material. And if X-rays are emitted from a single atom, and this X-ray will be carrying information about the chemical composition of an element. So basically XRF will give you information about elemental composition. So XRF is a powerful tool for qualitative as well as quantitative analysis. But please do remember that if atomic number is less than 8, that is below oxygen, you will not get any X-ray spectrum. In fact, it is a very weak signal you will be getting. So you cannot analyze using XRF these elements, especially the elements which are having atomic number much lesser than 8. So please look into this table again, X-ray XRF energy table, you can look into that. And up to the oxygen, you cannot even little higher also. You cannot see very clear. Of course, there are some cases a little amount of the peaks will be available, but it is really difficult for the detector to identify these elements. So below oxygen, it will be really difficult for us to identify the element. And XRF is a non-destructive technique. You don't need to break your sample. And in fact, there are two varieties of XRF is available with us. One is WD XRF, which we call wavelength dispersive XRF, and energy dispersive XRF. And what is this difference between wavelength XRF and ED XRF? ED XRF is working based on the energy dispersive principle, and most of the elements you can analyze. And there are some typical cases where the resolution will be a challenging for a researcher. So in that case, you need to go for WD XRF. You can resolve the peak very clearly if you are using WD XRF. Accordingly, the cost of equipment is also different. ED XRF and WD XRF, both are going to be different cost-wise also. And if we look into this anatomy of ED XRF or WD XRF, the X-ray tube will be there. X-ray, you need to create a X-ray generation is required, and which is made to fall on your specimen or sample. And the energy which is coming out, the X-ray which is emitted by your sample will be analyzed using a detector. And in case of a WD XRF, what we are going to do, in this case, the X-ray, from the X-ray source, make the X-rays to fall on your sample specimen. So X-rays will be emitted by your specimen. Now, we are not directly going to analyze them. In fact, resolve them based on their wavelength. So the emitted X-rays are of different wavelength based on your chemical composition. Say chromium, the emitted X-rays from chromium will be having certain wavelength. Nickel, the emitted X-rays from nickel will be different, having different wavelength. So separate them. How to separate them? Just pass through certain crystal. So here we have a single crystal, and this crystal will diffract your X-rays based on its wavelength. So you know very well, based on the Bragg's law, lambda is 2d sine theta, n lambda is 2d sine theta. So if lambda is different, naturally the angle of diffraction will be different. So you can make you can differentiate the elements by this way. So by this way, you can resolve the elements very clearly. So WDXRF will give you more accuracy in your analysis. And we need to create X-rays. For creating X-rays, we have sources. So you can use Coolidge tubes will be used. Usually, it's a vacuum tube. And inside the vacuum tube, you have a copper block, and high energy electrons will be impinging on this copper metal block or copper target. So X-rays will be generated out of it. Is it copper is the only way I can generate X-ray? No, I have various possibilities are there. You can go for molybdenum, copper, cobalt, iron, chromium, and so on. So commonly used in XRF tools or XRD tools, commonly used sources are, these are all the sources which are available to us. And even you can go for using a natural radioisotopes also you can use. Here are some list of the isotopes what you can use for generating X-rays. The X-rays which we generate from these sources are having a wavelength from 0.3 to 0.47 angstrom. So by this, you can very well analyze up to silver, and according to your requirement, you need to change your source. So there are sources like silver, moly, copper, nickel, cobalt, iron, chromium, and of course their wavelengths are different. And in each case, we need to use certain filters. So when we generate X-rays, the X-rays are not monochromatic. It is multiple wavelengths is there. So naturally, the results will be confusing if you are analyzing with the multiple wavelength. So what we need to do is we need to filter out what is additional X-rays which are coming out. Already we have seen that when you generate X-ray, K alpha radiation will be coming up, K beta radiation will be coming up, even K alpha 1 and K alpha 2 will be coming up. So we need to filter out so that we can use a single or monochromatic waves can be used so that our analysis will be better. Now, how to do this? We need to use filters. So filters, for example, zirconium, if you are using, this will filter out K beta lights so that you can use a monochromatic source. So as we said, the WDXRF will give you clarity about the resolution, or it can resolve your peaks very clearly, resolve your results very clearly. As you see in this image, so we have the X-ray source, and the X-ray source is made to fall on your specimen, and your specimen is giving rise to the X-rays. So X-rays are coming out from your specimen, and these X-rays are emitted by your specimen. So once you irradiate your specimen with X-ray, the X-ray will be emitted from your specimen. So this X-ray has its own character. So that's what we are going to analyze, and that will be passed through collimator. Collimator is basically allowing only the wavelength or the direction, fixing the direction, because the X-rays will be in multiple directions. So you can make the X-rays which are in a same direction may be allowed to fall through the crystal. So make it to fall through this crystal, and this crystal can now diffract. So based on your wavelength, it will diffract to various angles. You know well, n lambda is 2d sine theta. So based on your lambda, theta will be different. So you may place the detector will move in this circle. So where it can identify where it is diffracted, where your X-ray is coming up. So from this, you can identify what is the character of X-ray which is coming up, or what is the energy of X-ray, or what is the wavelength of X-ray. From this character, what is the element which is present that we can identify. And what is the crystal we use? In case of WDXRF, we are going to use a single crystal here. And what is the crystal we are using over there? So you can use a topaz or LIF, sodium chloride, EDT, or ammonium dihydrogen phosphate. So these are all the available crystal which is available with us. Their lattice spacing is very important because what kind of wavelength you are looking for your analysis, and what kind of a crystal you can analyze, what is the accuracy of your analysis. So all these things you can work out based on what is your material you are going to analyze. And once the X-ray is coming out, now we need to analyze them. We need to detect it. So there are detectors are there. These detectors will analyze the X-rays which are coming out. So there are detectors like maybe a gaseous detector, solid state detector, and many other types of detectors are available. So most olden technology, they were using ionization principle. X-rays will be ionizing the gaseous atoms. So measure or quantify the ionized species, and thereby you can quantify how much X-ray is emitted. And recent years, we are going for solid state detectors. They are much convenient for us, and relatively faster, accuracy is better, detectable limit is also much better. So you can use solid state detector. Accordingly, the cost will be different. So if you are going to purchase an XRF, and the cost of XRF depends upon what kind of detector you are going to use. Accordingly, your XRF accuracy will be also different. And we have various type of XRF instruments. You can have a portable, or you can have a handy type XRF, and you can have a desktop XRF, or you can have a larger one. And when you assemble these things, your X-ray source, detector, and everything in a compact way, naturally you have to compromise with the accuracy. So if you are analyzing with a handy model, accordingly the accuracy will be not very good. But for regular applications, regular like metal detection and all, if you want to use it, definitely you can use a handy model. And if you want to go for a really high accuracy, then you need to go for a desktop model or any other version. So already Dr. Ajita has covered about XRF sample preparations. So there are typical methods. So basically there is a procedure how to prepare your specimen. Make a pellet actually. So make a powder, and these powders will be either hold it in aluminum cup, or you can make a solid pellets. So basically we can mix it with some binders also. So according to your sample, you can make the preparations. If you have a powder sample, there are specimen holders are available, and these adhesive tapes also available. So you can spread the powders on the top, and you can load it in the machine, and you can go for analysis. And there are various kinds of fixers or the sample preparation techniques are available for us. And in the analytical techniques, when we are going to analyze XRF, X-ray is emitted now, XRF signal is coming out. So the XRF signal, when you are going to analyze XRF signal, this information is very important for us. So you cannot analyze the organic elements like hydrogen, carbon, nitrogen, oxygen. They do not give XRF peaks. So if you are going to work with these elements, and you may find out some better tools other than XRF, because the signal will be very weak if you are trying to analyze using XRF. And low atomic elements like chlorine, argon, potassium, calcium, they give only K peaks. And L peaks are actually very low in energy, and you will not be able to see the L peak from this. Only K peak you are able to see. And high atomic elements, K peak will be too high energy, so you will not be able to see very clearly the peaks, and L peaks will be visible. And in case of a middle atomic elements, so you get both K lines as well as L lines. So basically what we need to remember is K lines and L lines will be visible, K alpha, K beta, L alpha, L beta. So in case of low atomic elements, you can see only K alpha and K beta lines. And in case of high atomic elements, you will be able to see L alpha and L beta lines. And middle elements, you will be able to see alpha. So here is an illustration, your X-ray signal, XRF signal, how the signal will be coming. So XRF signal will be, this is the typical XRF signal from your specimen. So basically in X-axis you have the energy, because we are characterizing, or we are resolving the material based on the energy of X-rays. So X-ray emitted around say 8.5 and 9.2 and maybe around 9.8, and you can see the peaks which are at specific locations. Their energy is different. So you are getting peaks at different location corresponding to different energy. So this example is, we have taken a subsequent element, say for example, zinc, gallium, germanium, arsenic, selenium. So if you analyze this continuous in the periodic table, they are continuous. So if you analyze them, you can see that K alpha line of zinc, and similarly gallium, K alpha line of gallium, and K alpha line of germanium, K alpha line of arsenic, and so on. So according, one thing to remember, when the atomic number is increased, so the intensity will be increasing. Second thing, it is also depend upon the quantity. How much quantity is there in your material? So these two things are going to decide the signal of X-ray which is coming up. So the intensity depends upon this. So basically how we are going to characterize what is the location, where is the peak is coming up. So that is going to give information about the elemental composition. And what I can do is, instead of getting one signal from one location, I can scan the sample continuously from through the surface. If I scan the sample continuously from one throughout the surface, so I can get the composition, how the elements are distributed within my material. Say in this present case, we have a scan which has a cerium, iron, strontium distributed. So what is the distribution of cerium in your specimen? And what is the distribution of iron in your specimen? What is the distribution of strontium in your specimen? Very beautifully, you are able to visualize it, how they are distributed, where cerium content is more, where iron content is more. You can come to certain research analysis, you need this kind of information. So you can go for mapping of your results. So mapping will give you better idea about the chemical composition. And when we analyze this K line series, so in this case, you are able to see that only K lines are visible, K alpha and K beta is visible, and L lines are not visible. And one more thing we have to remember here, what is the difference between this energy? This is 10.53 kilo electron volt, and here at arsenic it is 11.73 kilo electron volt. Sometime it may happen based on your equipment. The equipment will not be able to resolve such smaller level of energy. So in fact, the energy difference is very close. So sometimes both the peak will get merged and it will look like a single peak. So one has to be very careful when you are analyzing based on your equipment. You may be wondering that I have arsenic in my specimen and arsenic signal is not coming up. And probably it is mixed with the K alpha line of your arsenic. So that one has to very carefully analyze that. So that one has to remember when you are analyzing the signal. And another thing when to remember in your analysis, the ratio of K alpha and K beta. Just look the height of the peaks, K alpha and K beta. The ratio is somewhat about 5:1. So this will be the signal ratio. Whereas if you look into the L alpha lines, L alpha reflection, L alpha and L beta, roughly the height of these peaks you can see 1:1. So in K alpha, K beta, it is 5:1. In L alpha, L beta, it is 1:1. And L lines will be more clearly resolved. So sometimes K lines may not be giving you, maybe mixed with something else. So L lines may give you intensity, may give you a better analysis for it. And similarly, so here is another complexity for us. So we have mercury and arsenic, and the third peak, you can look into the third peak, and K alpha, K beta of arsenic and mercury, both are merged together. So it is really difficult to resolve them. So there are some typical cases you may find some difficulty in your analysis. And similarly, the analysis results also, it depends upon what kind of detector you are using. So if your detector is not highly resolvable detector, so solid state detector recently developed like CMOS detector and all, they give you better accuracy. But older detector, they will not be able to give you better accuracy. So you are able to see the signal for the same specimen with the old detector and new SDD detector, how the lines are very clearly differentiated. So, and there are certain artifacts also coming up. So for example, you are analyzing larger quantity of iron is there in your specimen, or any other material is there in your specimen. Both reflections like K alpha of iron is coming at the same time. So they can combine with each other, and some peak will be coming up, which is 12.8 kilo electron volt. Actually, iron has the wavelength of energy of 6.4 kilo electron volt. But after combination, the some peak has a value of 12.8 kilo electron volt. So you get additional peak at a location of 12.8, which is not the reality of your specimen, but it is coming up due to summing up event. So that is due to larger quantity of your material. In such case, what you can do is reduce the quantity of the material so that your accuracy will be improved. And there are certain escape peaks. So in this case, it is a reverse actually. So both get subtracted and you get a peak at lower position. So this also artifact which is coming up. And also the artifact will be coming from the X-ray tube has certain tube material and other the window materials are there. So they can also come out, X-ray can incident with the X-ray tube materials, and it can give you signals of these. So one has to be aware of these, where from these peaks are coming up. So you can use XRF is a powerful tool, and it is relatively easy tool, and it is a convenient tool for a researcher to identify the chemical composition. You can use it for geological application or environmental application or any recycling of metal or waste products, waste materials, and many other miscellaneous applications like archaeology and other forensics applications also you can use. And what is the limitation of XRF? XRF has a certain interference. Not all the elements will be a problem. There are some typically certain elements where you can find the interference between two elements. And there are cases, if you want to measure the sub ppm level, then definitely XRF is not a suitable tool for you. You can look into other tools, other techniques for sub ppm level. And in ppm level, yes, XRF is a highly accurate and efficient method for us. And in the similar line, we have another tool, another powerful tool for us to find out the crystal structure or atomic arrangement in the material, which is XRD, X-ray diffraction. So here is a typical image, diffraction image you are able to see. So we should thank Lave, because we have studied in basics of X-ray, XRD, where how the crystals will be diffracting, and all those details we have studied. Materials are made of crystals, and the crystals have regular repeated arrangements in 3 dimensions. So all these things we have studied. So what Lave thought, if this concept is clear, if this concept is true, that is materials or the crystals are having a repetitive arrangement of atoms within them, a regular arrangement within them, then they should act as a grating. So they should involve in the act of diffraction. So they should diffract a wave actually. So this is first idea he had. So if we are considering a crystal is regular arrangement, then it should diffract, because the atomic planes should act as a diffracting, it should act as a diffracting incidence, it should act. And the second question is, X-rays are waves or particles? And there was a larger discussion about it. And if it is a wave, if X-ray is behaving like a wave, it should get diffracted through a crystal. So both these questions should be answered. And with this idea, Lave has started his experiment. He kept a crystal and passed X-ray, and he recorded the diffraction event. So of course, the image provided here is not the actual image what Lave has got. Lave has got center beam was dark totally, but he could get the diffracted patterns. So you are able to see spots. So there is a central beam, and around which there are many spots are available, and these spots are coming up from the diffraction. So crystal has many planes, and these planes from where the diffraction is taking place. So we are able to see the diffraction pattern. So if you want to, if you carefully calculate and you can come to a conclusion what is the crystal structure is of, what is the atomic arrangement in this material, you can come to a conclusion. So what we do is we use X-ray to identify the atomic arrangement in the crystal. So this is another beautiful tool for us. XRD is another beautiful tool for us. And there are different techniques for XRD techniques, X-ray diffraction. So basic or the first introduced technique is Lave method, and subsequently powder method, rotating crystal methods are available. In case of Lave method, we are varying the lambda. You know that lambda is 2d sine theta. So where the variables are, lambda can be a variable, theta can be a variable. So if you are fixing this theta, fix the crystal. So you can take a single crystal and fix this crystal. Theta is fixed, angle of incidence is fixed, and vary the lambda. So you can get diffraction at different locations. So this is one way, that is by Lave. And second method is by powder method. In powder method, place a powder. So if you look into this powder, there are too much of crystals will be available, number of crystals, it is polycrystals. So numerous crystals will be there, and each crystal is going to diffract. So there are number of diffraction events we are going to face. So in this case, when you are using a powder, we are going to fix the lambda. Lambda is fixed, and we are going to vary the theta. So vary the theta and make different planes incident with your X-ray and get the diffraction pattern. So this is powder diffraction method. And in case of a rotating crystal method, you can use a single crystal and you can fix the lambda and vary the theta. So that is another method. So there are various techniques for X-ray diffraction. So the basic components again in X-ray diffraction, we have X-ray tube and we have incident beam optics, because in general to talk about, you need X-ray tube, you need goniometer and detector. These three things are very important. A source, sample and detector. These three things are important. And the X-rays need to be processed before incident on your specimen. X-ray should be processed so that you get a monochromatic and a proper X-ray incident on your specimen. So incident beam optics will be used, certain optic materials, and there is a goniometer over which your detector and your source and sample will be located, which I will be talking about. And receiving side also, there are certain correcting tools, correcting the X-rays which are emitted. It need to be amplified and analyzed. So you need optics on the receiving side also. So essentially you have a X-ray tube and the sample holder and the detector, and you have optics. And what is this X-ray source? We have discussed in detail about the various types of X-ray sources. So where high energy electrons, when they impinge on the surface of the metal target, X-rays will be produced. And X-ray sources, if you look into the XRD, there are two kinds of sources are normally practiced or normally used. One is sealed X-ray tubes, where it is operated in the range of 1.8 to 3 kilowatt. And in case of a rotating anode, you can use the X-ray. You can operate in the range of 9 to 18 kilowatt. Now, what is the difference? If I use a 9 to 18 kilowatt, naturally I can get intense X-rays coming out. If I use a low power, I can get only limited amount of X-rays coming from my material. So that is the difference actually. And if you are using a single sealed tube X-ray, if your electron beam is incident on your target material, it is a single spot. So it can easily melt because, as we discussed, 99% of your energy is going to convert into heat, and only 1% is, or less than 1% it is. So in fact, proper calculation says it is about 0.1%. So only such amount of energy is used for X-ray generation. Remaining energy is converted into heat. So the heat will melt your target material. So you need to continuously cool it. So in a sealed X-ray tube, you cannot use a high power because your target will get melted. Whereas in case of a rotating X-ray tube, it is rotating now. So relatively cooling effect will be better. So you can relatively use a high power in this case to get high power X-ray from the source. So basically in both these cases, the target material will be subjected to water cooling because such heat must be continuously removed. And the target material, as we discussed, you can use a molybdenum, copper, iron, chromium. Most cases, almost 90% of X-ray equipment, whatever you see in various universities or research laboratories, you will be seeing copper as a target. And rarely you will be able to see moly or iron or chromium. So according to the application, the target material will be different, but copper is the most commonly used one. And if you are using a moly target, and the voltage applied will be about 50 to 55 kV, and in copper and other material about 25 kV is the operating voltage. And the wavelength of X-rays are different based on your element. Already we discussed about it. You can use various material like silver, moly, copper and all, and accordingly their wavelength will be different. So analytical, what kind of things you are going to analyze, that will be different. And copper will solve almost most of the analytical purpose it will solve. And when the incident beam when X-ray is coming out from your source and they look into this X-ray, it is not in the single direction. So they are in multiple direction. You need X-rays coming up from these in the same direction so that the analysis will be better. So you can use certain divergence slits, or you can use certain collimators or solar slits. So by using this, you will be able to make the X-ray which is coming out, falling on your specimen will be having a single direction. And you can use refocusing optics basically. So to focus X-ray on your specimen. So usually it is parabolic mirrors. So you can make it to fall on your specimen. And another important thing is we are going to remove unwanted wavelength. As we said, we have K beta, K alpha 1 and K alpha 2. It is relatively easy for us to remove K beta and K alpha, whereas it is really difficult for us to remove K alpha 1 and K alpha 2. And if you want to remove this K alpha, because the difference between their energy is very, very thin, very low. So K alpha 1 and K alpha 2 separation is really difficult for us. So what we use is the optics what you are going to use, or the monochromator what you are going to use will be really costly. So most cases K alpha 1 and K alpha 2 will be there, but K beta you can remove it. So we are going to use certain kind of a filters, and these filters will do this job. So for example, if you look into this copper K alpha and copper K beta. So look into this K alpha line, which is 1.54 angstrom, and K beta, it is 1.38 angstrom. And just if you look into the nickel material, nickel absorption, it is 1.488, exactly in between the K alpha and K beta. So if you are using a nickel plate in the path of X-ray, it will filter out certain wavelength. what kind of wave it is going to filter out? So the waves which are less than 1.488, which is K beta. So nickel filter will remove almost 99% of copper K beta line and 50% of K alpha line. So please do remember the intensity of X-ray is also reduced. So if intensity of X-ray is reduced, use a effective detector so that your signal will be strong enough. What kind of information you are getting, that will be very clear enough for you. And here is the elements, and here is what is the kind of filters you can use. Say, if you are using silver, and usually the element is just below the element just below of its atomic number. So for silver, you are going to use a palladium, molybdenum, you are going to use a zirconium, copper, nickel. So likewise, you have various filters which are available, and there are few commercial filters which are there in the market as well. Say, for example, here is certain kind of a common filters, nickel filters. So even after filtering out, K beta line is visible to you. And if you are using some latest detector where you can notice that it is completely removed, K beta lines are completely removed. So the X-ray equipment, what kind of equipment you are going to use, that's going to decide the quality of X-ray which is coming out, or quality of the information what you are getting from your material will be having a more clarity and accuracy. And similarly, another problem we encounter with, what is the problem we encounter with? So when X-ray is incident, it fluoresces. So this is another typical problem we face. So basically, due to this fluorescent event, so two things happens. One, it is going to absorb the X-rays and decrease the intensity of incident X-ray. That is one thing. So effective X-ray which is falling or which is giving information from your material will be reduced. And the second thing is the fluorescent X-ray will increase the background, and background noise will be increasing. So the signal clarity will not be there if you are having a material of fluorescing material. Say, for example, if you are using the cobalt and the subsequent one, that one iron will give fluorescence. So you need to be, in this case, if your material is having more noise in your X-ray peak, then better use a target material of different target material. Say you are analyzing your material with copper and you get more kind of noise in your material, either go for better detector or you can change the target material. So here is a typical illustration. Say, for example, hematite is analyzed here with 1D detector. So again, I will come to this part detector, one line detector and point detectors and all. Point detector is lower version, line detector, area detectors are higher version in X-ray equipment. So basically, if you are using a line detector and your signal, you can notice the signal from the hematite, you can notice the background noise is much higher and the signal is weak actually. And by properly using a proper detector or the target material, so you can increase the signal intensity and the clarity will be more. And similarly, when you are working with X-ray, please do aware about the safety. So when X-rays are produced, or when X-ray first time X-rays are generated, X-ray torches were being produced, and people were playing with these X-ray torches, they used to see their bones, because if you make it to fall on your hand, you can see your bones. So they were playing with these kind of torches, and later it was realized a lot of health issues, especially cancer due to X-rays. So when you are working in X-ray room, you should be very careful. So be aware about how much X-ray is emitted. So it is always recommended when X-ray machines are installed in any location. So there should be some counter, so where it will indicate to you about the X-ray which is in that room. But still, we are making all safety in X-ray. Here is the typical X-ray tube, and in this X-ray tube, as you see here, X-ray copper target is there, and which is continuously cooled. And here is a shutter, and this shutter is usually you can make use of a beryllium, and the thickness of this material very carefully decided. You can calculate what should be the thickness of this material window which is being used. So by using this relation, you will be able to calculate what is the thickness. So here is the typical illustration. If I am using a copper, I need 1 mm thick, but still I am able to absorb only 81% of X-ray which is coming out. And if you are using a beryllium, even 0.125 micron will give you 99% of X-rays will be stopped coming out from your X-ray tube. So already it is carefully designed. X-ray equipments are very carefully designed, but still one has to be careful when you are working with X-ray. Don't expose to the X-ray for long time. And once you place your specimen over there, come out of the room, and once it is completed, you get signals. So then you can stop the X-ray and you can enter into the room. So that is a much better or safe way to operate X-rays. So another typical or important thing is the design, how the diffractometer geometry is designed. So basically, if you look into the X-ray, as we discussed, you need a source, you need a detector. So you place the source here, you can place the detector here, and here is your specimen or your sample, you are going to keep it, and you X-ray incident on your specimen is going to come to the detector. And exactly it is balanced. We do certain calculation about the angle of diffraction and all. So now in this case, here is the angle 2 theta. So again, please do remember, when the X-ray is incident, the X-ray is emitted from the plane, not from the surface of your specimen. Please, most of the students used to think that X-ray is emitted in XRD. X-ray is emitted from the surface. No, it's not coming out. Diffraction is not coming out from the surface. Rather, it is coming from the plane. The orientation of plane will be different. It may be in different direction. So X-ray incident over to the plane is going to diffract, but it is imaginary. Where is the plane? You do not know. From where it is reflected, you do not know. So how you are going to calculate the 2 theta? So in that case, what we are going to do is the transmitted beam, we know where it is transmitted, and the diffracted beam. So from this, the 2 theta will be worked out. So that's how the movement of detector and source will be done in the design. So basically, we can draw a circle connecting all these 3: source, detector, sample. So connect all them together. This is what we call focusing circle. So when you design X-ray, this focusing circle is very important. And you have this Brack's angle. Just now we discussed about the Brack's angle. Brack angle is actually the plane in your specimen, not the surface of your sample. And what you can do is keep the specimen at the center and source and detector in the periphery of it, and draw a circle. Now, if you draw a circle, you get a circle, and this is what is we call diffractometer circle, and this is what we call goniometer. So when we design X-ray, this goniometer is very important. What is the diameter of this goniometer? Because it is the circle where you can collect the information, where your source you need to fix it, where you need to fix your detector. So this is, and where you need to fix your specimen. So this is connected by this diffractometer circle. So exactly at the center of diffractometer circle, you place your specimen, and at the circumference, you have your source and your detector. So this is how the geometry or the design is there. Now, the diameter is very important. Goniometer, what we are talking about is this goniometer. So this goniometer diameter is very important. If this goniometer, if it is 140 mm, or if it is 180 mm or 240 mm or relatively larger one, so you can design various diameter, and if the diameter is larger, your accuracy will be much better. If you can design smaller and smaller equipment, you are compressing this diameter. This goniometer circle, you are compressing it, you are making it into smaller. So when you are making it into smaller and smaller piece, naturally the detection limit will be, you have to compromise with the detection limit. So sometimes the 2 theta will not be resolved very clearly. So that one has to remember about it. So there are different types of scans are available. So we have theta 2 theta scans, and we have theta theta scans, and we have omega scan, other type of scans are available, which I'll not be going very detailed because of the time limitation with us. And you have you have different types of X-ray which is available. You have a omega rotation, you have kappa rotation, you have alpha rotation, you have a pi rotation. So basically, you can rotate the sample in various direction. So this is required if you are analyzing your specimen about the orientation. So sometimes you are making a silicon epitaxial film. So whether my film and the base material is properly aligned in the same direction, or they are having different direction, or you are making a material where you are making a single orientation. So single crystal you are making it, or a polycrystal oriented in a single direction. So if you are making materials having different orientation, and for such orientation studies, this kind of tools will be efficient or effective for you. So multi-axis goniometer is also available. So what we have discussed is goniometer design, and in fact there are various designs are possible, and this typical design is what we call Bragg-Brantano parafocusing geometry. So in Bragg-Brantano parafocusing geometry, say you have your material. In your material you have planes, plane 1, plane 2, plane 3. Their d-spacing is d1, d2, d3, and their reflection, when they are diffracting, and the diffraction will be focused on the circle. So you are able to see the red circle if your specimen is having d1 spacing, d2 spacing, it's goniometer circle, and d3 spacing, your goniometer circle. These are all the locations where you are going to get the signal. Your detector can find out the signal. But all these signals, all these circles, they are interfering with the goniometer circle. So you are able to see whether it is blue one or the green one or the red one, they are lying at this circumference. So this is the design when you design Bragg-Brantano parafocusing geometry. So this design is very important for us. So as we discussed, so here is a typical photograph of your X-ray machine, XRD, X-ray diffraction, where you are able to see the source. Here is the source, X-ray source, or you can call X-ray tube. And from this X-ray will be generated, and you have optics through which X-ray will be processed and it will be transferred to the sample. So you keep your sample at the center, and the detector is this side. You are able to see the detector. So X-ray falling on your specimen will be diffracted, and the detector will be detecting it. So basically, it is all these source, sample, and your detector. They are arranged in the circle. So this circle is what we call goniometer. So our goniometer circle. So this is very important in the design, and the diameter of this goniometer is very important. And we have various possibilities like parallel beam arrangements, and many more arrangements are there. So in case of a parallel beam geometry, sometimes what we do, we pass X-ray at very low angle, and the detector will be moving at an angle of 2 theta. And there are some grazing incidents. So in case of a grazing incidents, the X-ray source will be made to fall on your specimen at very low angle. So normally it is 0.2 to 5 degree angle. And by this way, what you can do is you can restrict the penetration of your X-ray. So X-ray will be penetrating only to the top of your specimen. Say you are having a thin film of your material. So X-ray need to be penetrated only a short amount, that is maybe 10 nanometer or few 10 nanometers, maybe 40 nanometers, 100 nanometers. So you want to get signal from the top of your specimen, surface of the specimen. You can use a grazing incidence X-ray diffraction. So by this way, you can get the information, you can get the signal from there. And regular powder, regular XRD is different, and this grazing incidence XRD is different. And there are tools like divergence slit, and these divergence slits are going to control the amount of X-ray beam which is falling on your specimen. Say for example, here is the incidence, X-ray is falling on your specimen. You can notice the penetration depth, the angle of incidence and the penetration depth, they are different. So if it is falling at a high angle, the penetration depth will be different. So basically, the volume of the material which is incident with X-ray is very important. So where from you are getting the information, where from your X-ray is emitted, or where from it is coming out, the volume of your material, from where you are getting the signal is important, especially if you are working with the quantitative X-ray analysis. If you are quantifying the phases, or if you are working with certain quantitative analysis, so this is important. And you can look into this you can control by divergence slit. So as you see here, if I use a divergence slit of 2 degrees, then the beam length will be 35 mm. And if I use a divergence slit of 1 degree, then you can see that it is about 15 mm. So accordingly, the specimen irradiated with your specimen will be different. So how much amount of material we are going to use? Only very few milligram or amount of sample we are going to use it. And we use different type of detectors. In general, you have a detectors like scintillation detector and solid state detector. In general, let me conclude in a way like point detector, line detector, and area detectors. What is this point detector? You have a silicon chip. So X-ray which is coming up or emitted from your specimen or diffracted from your specimen is incident on this silicon chip, and it is counting as a emitted X-ray will become counted as a photon. So likewise, every point will be counted. Every signal will be counted in a point wise, and it will count total number of points counted from a single energy, and it will be making X-ray. The diffraction pattern will be made for us. And in case of a 2D line detectors, so it has 160 silicon chips will be there, and all parallelly will be detecting. So by this way, your accuracy will be much better. Rapidly you can process the material. And in case of area detector, you get much more accuracy. So your material will be easily detected. So here are some latest detector where you can use an area detector, and 2-dimensional detectors are available. So you can get very clear signal. There are some signal which will be missed by point detector, whereas line detector will give you better accuracy. And there are different methods for X-ray performance. So you can go for X-ray powder diffraction, single crystal diffraction, or back reflection, or grazing incidence, or X-ray reflectivity, or small angle scattering. So most commonly 90% of the people, they use powder diffraction because you want to know the phases. What is the phases which are present? What is the quantity of these phases? And what is the unit cell? What is the structure of the material? What is its crystal? And when I make maybe a perovskite material, if I dope it, what happens to the material? What happens to the structure of the material? Where the atom is sitting? So those kind of information you can get. Even you can get information about the crystallites. What is the crystallite which is available? And by doping or by other processing, what happens to my crystallite? Whether it is increasing or decreasing in size, and what is the orientation of this crystal, and what is the strain in this crystal, lattice strain in the crystal. Is there any defect in the crystal? What is the quantity of defect which is there in the crystal? And what kind of texture it is forming? And any residual stresses there in your specimen. So all these information you can get from powder diffraction. And by using a grazing angle diffraction, you can get information about the surface. If you are working with thin film, and especially the lattice mismatch between the film and substrate, so this grazing incidence diffraction will be useful. And epitaxial work or micro strain in your films, and reciprocal space mapping. So there also it will be usable. And there are, in grazing incident, there are various methods like coplanar and non-coplanar methods are available for us, especially if you want to find out how the film is distributed, how the orientation is there, and there you can use it. And some cases you can use X-ray reflectivity. So similar to other light waves, X-ray get reflected. This you can use it for finding out the coating thickness, or some films and surface roughness of a material, where you can use X-ray reflectivity. And even back reflection Lave method is also used for some applications where you can use them also. Sometimes you need to analyze pores in your material, nanopores in my material, and I want to use polymer and all. So cellulose-based material. So there, your information you need to collect from 0 to 5 degree or less than 10 degree. So in such cases, what you need is small angle scattering incidence you need. It is not that every X-ray equipment will work for you. No, that is some equipment, all the provisions will be available. Then in most equipment, small angle facility will not be available. So if you want to find out what is my pores, nanopores in my material, and I want to get information below 5 degree, then better go for small angle scattering incidence. So which will give you information about crystallinity of polymers, organic molecules in solution, and it also gives you information about structure and other porous information and all. And you can also use single crystal information. Yeah. So with this, I'll stop here. If any question, please.